In the mid-1990s, NVIDIA was just another startup. No legacy, no guaranteed future, and no successful products. It was a gamble. Three engineers, Jen-Hun Huang, Chris Malachowski, and Curtis Priam, bet everything on 3D. Today, that gamble has paid off. NVIDIA GPUs power the gaming PCs that deliver cinematic realism to millions. They are the silent engines of global data centers, processing the world's most complex and vital data. And they have become the indispensable backbone of modern artificial intelligence, training the models of our future. This is not just the evolution of graphics cards. This is the story of how NVIDIA survived failure and became a giant. In the early 1990s, graphics acceleration barely existed. Computing was a flat, two-dimensional world. Most games relied almost entirely on the CPU for every calculation, from physics to the visuals you saw on screen. Graphics cards were simple output devices, handling basic 2D output. 3D gaming was little more than a dream. NVIDIA was founded in 1993 with a bold vision, dedicated, specialized hardware for 3D graphics. Their first product arrived in 1995. It was called the NV1, and it was incredibly ambitious. It supported advanced features like quadrilateral rendering, a unique and experimental approach to 3D visuals. It even featured integrated audio, aiming to be the complete soul of a mid-90s gaming machine. But there was a fatal flaw. Developers began to standardize around Microsoft's Direct 3D. NV1 did not. Developers didn't adopt NVIDIA's approach. The card failed commercially. Their next project was cancelled. By 1997, the company was dangerously close to running out of money. It was their final chance to survive. They needed a comeback. They abandoned experimental curves for industry standards. That comeback was Riva 128. This time, they focused on performance and compatibility. It was fast, supported Direct 3D properly, and was affordable. It sold well. NVIDIA had survived. Then came Riva TNT and TNT2. These cards introduced 32-bit color and improved drivers. The difference was night and day. Games looked more realistic than ever before. NVIDIA was winning. In 1999, NVIDIA released a card that changed everything. They didn't call it a graphics card. They called it a GPU, Graphics Processing Unit. The GeForce 256 was born. For the first time, hardware transform and lighting were handled directly by the GPU. This took the load off the CPU. Games could now have more geometry, more lights, more life. The GPU was no longer optional. It became the essential heart of every gaming PC. But success brought competition. The early 2000s saw the rise of a powerful rival, ATI. The pace was relentless. Every 6 months, a new card, a new king. The war was on. With the GeForce 3, programmable shaders arrived. Developers could now write code for the GPU. Games transformed from blocky toys into realistic worlds. NVIDIA was leading the charge. But in 2003, they stumbled. The GeForce FX series was a rare misstep for the company. It was loud, hot, and struggled to compete. ATI took the lead. It was a wake-up call. NVIDIA responded with the GeForce 6 series. They didn't just catch up, they leaped forward. SLI allowed gamers to link two cards together. Power was the only thing that mattered. And then, in 2006, they released the legend. The GeForce 8800 GTX. It introduced unified shaders. It wasn't just faster, it was smarter. It changed the architecture forever. But hidden inside was something even more important. A platform called CUDA. This allowed GPUs to do math, not just graphics. It was the seed that would grow into the AI revolution. NVIDIA had conquered gaming, but their biggest transformation was yet to come. NVIDIA had survived its infancy, but the path to global dominance would require a complete rethink of what a GPU could be. In 2010, NVIDIA released the Fermi architecture. It was their most ambitious project yet, built for massive parallel processing. It was designed for brute force, pushing the boundaries of transistor density to provide a massive leap in compute power. But that power came with a heavy thermal cost. Fermi ran hot, so hot that the GTX 480 became a target for industry jokes. Fans had to spin at extreme speeds to keep the card from melting. It was a technical triumph, but a consumer challenge. Despite its heat, Fermi was a breakthrough for science. Its unified memory architecture was a gift to researchers worldwide. This era pushed NVIDIA deep into the high-performance computing market. The GPU was officially moving into the data center. Learning from Fermi, NVIDIA pivoted. The new goal was performance per watt. The result was the Kepler architecture. Kepler and the subsequent Maxwell architecture delivered unprecedented efficiency. High-end gaming could finally fit into laptops. The GTX 900 series became a massive success. GPUs were getting cooler, quieter, and more accessible to everyone. NVIDIA now held a dominant lead in the consumer market, but they were about to release their greatest hit. In 2016, Pascal arrived. It was built on a new 16-nanometer process, allowing for a massive jump in transistor count. The performance jump was legendary. Gamers saw frames per second climb to heights previously thought impossible. The GTX 1080 became an instant legend. A card so powerful it remains a benchmark for value even today. For many, it was the perfect graphics card. But NVIDIA was already looking beyond just gaming. While gamers played, a revolution was beginning in labs. Pascal became the backbone of the deep learning explosion. Researchers discovered that GPUs were the perfect engine for neural networks. NVIDIA was no longer just a gaming company. In 2018, NVIDIA made its biggest gamble since the Riva era. They introduced Turing, and with it, RTX. Real-time ray tracing, the holy grail of graphics. It allowed for physically accurate light, shadows, and reflections. For the first time, games could mimic the behavior of light in the real world. But the performance hit was massive. To solve the performance problem, NVIDIA turned to AI. They launched DLSS, Deep Learning Supersampling. Using dedicated AI hardware, the GPU could now predict and render frames with incredible intelligence. The early days were controversial. Many gamers felt the tech wasn't ready, but NVIDIA stayed the course. They bet the entire future of the company on the idea that AI-driven rendering was the only way forward. Then came 2020. The Ampere architecture launched in the middle of a global supply chain crisis. Despite the shortages, Ampere delivered another huge leap. The RTX 30 series became some of the most sought-after tech in history. In 2022, Ada Lovelace arrived. The RTX 4090 was so large and powerful it redefined what a flagship card could be. With DLSS 3, NVIDIA introduced frame generation. The GPU was now using AI to create entirely new frames from scratch. The GPU had evolved into a complete compute engine, powering robotics, autonomous cars, and the world's AI. NVIDIA's data center revenue began to dwarf its gaming division. The world's economy was now running on their silicon. They were no longer just a hardware provider. They were the architects of the artificial intelligence age. From thermal struggles to total efficiency dominance, NVIDIA had redefined the rules of the game. The foundation was complete. Now, NVIDIA was ready to lead the world into the future of intelligence. But there were storms along the way. The rise of cryptocurrency turned the GPU market into a wild frontier. Demand skyrocketed, making it impossible for gamers to find cards. NVIDIA had to balance a divided market. They also experimented with mobile gaming, trying to put the power of their GPUs into the palms of our hands. The Tegra processor would eventually find its way into the world's most popular hybrid gaming console. NVIDIA's tech was now everywhere, from your pocket to your living room to the most powerful computers on Earth. NVIDIA had built the hardware. Now, the world was about to change the way it used it. A new era had arrived. This is the story of how a graphics company became the heartbeat of the modern world. The explosion of generative AI changed everything overnight. The entire world suddenly needed NVIDIA's compute power. Models like ChatGPT required thousands of GPUs working in perfect harmony. The demand was unprecedented. From Silicon Valley to every corner of the globe, the race for artificial intelligence was on. Compute had become the new oil, and NVIDIA held the keys to the most productive wells on Earth. With the Hopper architecture, NVIDIA delivered a specialized engine for the transformer models that power modern AI. The H100 became the most sought-after piece of silicon in history, powering the training of the world's largest models. It delivered an order of magnitude more efficiency, allowing for AI training at a scale never before possible. Dedicated transformer engines inside the chip were specifically tuned for the new language of machines. Then came Blackwell, a monster of a chip designed to be the engine of the next industrial revolution. Blackwell pushed the limits of physics, connecting two of the world's largest dies into a single, unified powerhouse. It wasn't just a chip. It was the foundation for AI factories capable of processing the data of entire nations. With massive power comes massive heat. Blackwell ushered in a new era of liquid-cooled computing at scale. Beyond the data center, NVIDIA's AI began to take physical form. The Isaac platform brought intelligence to robotics. Robots could now learn in simulation before ever touching the real world, accelerating the future of industry. NVIDIA's Project GR00T aims to provide the foundation for general-purpose humanoid robots that can learn from us, giving machines the ability to see, understand, and navigate the world just as we do. The same technology was applied to the streets. NVIDIA Drive turned cars into supercomputers on wheels, processing billions of operations every second to ensure safety in a chaotic, unpredictable world. The vision is clear: a world with zero accidents, where the car is a safe, intelligent companion. Powered by chips like Thor, the future of transportation is being written in NVIDIA silicon. With Omniverse, NVIDIA created a digital twin of the world, a sandbox for industrial design and climate science. Whole factories are now built and tested in the digital world before a single brick is ever laid in the physical one. Earth, too, uses this power to predict climate patterns with unprecedented accuracy, helping us prepare for a changing planet. A shared virtual space where researchers from across the globe can work together in real time. In healthcare, NVIDIA's AI is accelerating drug discovery and mapping the human genome at breakneck speeds, saving lives by helping doctors see patterns that were once invisible. This is the human side of the silicon. AI-powered surgery and diagnostics are making healthcare more precise and accessible for everyone. Looking further, NVIDIA is bridging the gap to quantum computing, preparing for the next leap in human intelligence, helping us build a more sustainable future through the power of simulation and data. Silicon for a greener Earth. What began with a failed NV1 in 1995 has become the foundation of modern computing in 2026. NVIDIA didn't just evolve graphics cards. They redefined what a computer actually is and what it can do. They have built the soul of artificial intelligence, the engine that will drive the next chapter of human history. The journey is complete. But for NVIDIA and for humanity, the evolution is only just beginning. This is the story of NVIDIA, the company that changed computing forever. Thank you for watching. At the end of the day, it's not about the what's. It's about the boundless potential of human imagination. NVIDIA, powering the future of everything. The evolution continues.